Okay, Bismillah ar-Rahman ar-Rahim. Okay, this is the second example. What do you have here? We have a pulley. Okay, a pulley. We have a rope or string attached to a spring to the floor, and on the other side, the rope attached to a small mass. Let's call it M, degree of freedom X. Okay, and the pulley is allowed to rotate but not to move, and the rotation we will give it theta. Okay, the degree of freedom. Here we have spring K. Okay, so this is the pulley with a radius R and mass moment of inertia given J. So this is given J, M, small m for the mass. Okay, degree of freedom X for the small mass, theta for the pulley, K for the spring, J for the pulley. Okay, all right, this is my system. Assume X and theta are measured from equilibrium position. Okay, this is the assumption. What does it mean, equilibrium position? Okay, the weight of the mass has nothing to do with the equation of motion. Keep this in your mind. All right, all right. What's this is given? Okay, find the equation of motion of the system and the natural frequency of the system. Okay, all right, first use which one you want to start with. Let's start with the energy method. Energy method. Okay, can we find the equation of motion using energy method for the system? The answer is yes. Why? Because we have no damper in the system. The system is conservative. Okay, what do we need for energy method? As usual, we need to find the total kinetic energy and the total potential energy. Kinetic energy, look at the masses, the moving masses. We have two masses, this one and this one, the pulley and the mass, the small mass. The small mass, translational motion, m x dot squared. The pulley is only, there is rotation here, no translational, right? So it's going to be half j theta dot squared. Good, that's all. Potential energy only from the spring, so it's going to be half k. What is this distance? This one. Okay, this one is the same as this one, right? We are assuming the rope or the string is not slipping around the pulley, okay, and unstretched. You cannot stretch it. Also, there is assumption here, I forgot to tell you, theta is small. Theta, this theta is small. What does it mean small? Remember from math, when theta is small, that means what? That means cosine theta is almost equal to 1, and sine theta is almost equal to theta. Okay, so this distance is how much? This one. This one is r sine theta, right? R sine theta. This one, this small distance. We're assuming vibrations, ya shabab, here. Vibrations. Vibration means very small displacement. So r theta, r sine theta, this one, r sine theta. Okay, this one will be what? Theta. Okay, because theta is small from the assumption. Okay, from the assumption, let me write a line here so you don't get confused. Okay, so the only potential energy half k r squared theta squared. Good? Okay. All right. So to find the equation of motion, summation of the total kinetic and potential energy must be equal to 0 all the time. So the time derivative, oh, not 0, sorry, Ashao, this is constant. Constant, not 0, constant. Okay, so the time derivative of the total kinetic and potential energy must be equal to 0. Okay, I forgot from the previous example. Oh, I said here 0, it's not 0, Yeshua. This is constant, okay? Constant, sorry about this, okay? This is constant. Constant, okay? This is constant, so the time derivative is equal to 0. Okay, here constant, so the time derivative equal to 0, okay? All right, so the time derivative, the total, what's the total? We have m x dot squared plus half j theta squared, okay, plus half k r squared theta squared equal to 0. Okay, find the time derivative. It's going to be m x dot x double dot plus half, not half, sorry about this, j theta dot theta double dot plus k r squared, theta will be theta dot equal to 0. Okay, all right, see, both we have theta and x on the same equation. I forgot to ask you here. Okay, find the equation of motion in terms, I have to pick one only, in terms of theta only. Can I ask this question? In terms of theta only. Can I ask this question? In terms of theta? Wait, how many degrees of freedom we have here? We have x, we have theta. Okay, we have x, we have theta. But in fact, both of these 2 degree freedoms depending on each other. In other words, there is a relationship between x and theta. You cannot move x without moving theta, and you cannot move theta without moving x. They depend on each other. That means we have only 1 degree of freedom. What's the relationship between x and theta? Okay, x is equal, this x, this displacement is equal to r sine theta, right? So theta is small. What does it mean, say theta is small? This will be equal to theta, r theta. Why? Because theta is small. This is from the assumption here. Okay? Theta is small. So x is r theta. So x dot r theta dot. So x double dot r theta double dot. Good? I'm going to substitute these values in the equation of motion here and get one equation of motion in terms of theta only. I can do this. Okay, I can do this. Okay, so I'm going to substitute theta here. Where is theta? X and x dot are theta dot. Okay, so let me write it here. The equation of motion. X. Let me go back. Mx dot x double dot. Let me write it again here. Mx dot x double dot. Okay, what else? J theta dot theta double dot plus k r squared theta dot equal to 0. Substitute x equal to x dot equal r theta dot and x double dot r theta double dot, right? So this will be m r theta dot times r theta double dot, right? Plus j theta dot theta double dot plus k r squared theta dot equal to 0. What's common here? What's common? Common theta dot, right? Take it outside. Okay. Then you will have m r squared theta double dot plus j theta double dot plus k r squared theta equal to 0. Okay, theta dot is not equal to 0 all the time. So this equation, m r squared plus j times theta double dot plus k r squared theta equal to 0. And this is your equation of motion. We got it. Okay? This is the equation of motion. Okay? All right. Can you find the natural frequency? Yes, the natural frequency will be how much? Let me write it here because it's very easy. The natural frequency, square root of what? This coefficient, kr squared, divided by this coefficient. We call this, by the way, we call this effective mass, the effective mass. This one is the effective mass, okay? This is the effective mass, we call it in vibration or in system dynamics. mr squared plus j. Okay? We got it. All right. Now we're going to do the same thing. Find the equation of motion, but we're going to use not the energy, sorry. Not the energy. We're going to use Newton second law. Can we use the Newton second law? Always we can use the Newton second law. However, for Newton second law, we need to draw the free body diagram. So start with the pulley and show the mass here. Show the degree of freedom, this one x. Show the degree of freedom here. We have a theta and we have j, don't forget j. Okay, we have the radius r. What else we have? Now show the reaction forces. We have a reaction force from the string here, or the rope going up. Same one. Oops. Same. Oops. What happened? Okay. Same force will be here. How do I know the same force here and here? This is tension. I don't know how much this tension. Okay, I'm going to call it T. This force, I'm going to call it T. I don't know how much is it. I'll take care of it next. But I'm going to call it T, the tension here inside the rope. One up and one down. How do I know one up and one down? From Newton's third law. Newton's third law, for any element, if there is one force on one end, the other force will be the same but opposite direction. Okay? All right. And this pulley rotating this side. So here we have a reaction force from the spring, always against the motion of theta. And it will be K how much? R theta. Okay, R theta. Good? That's all. So this is the free body diagram. That's all. Okay. Now we're going to use the Newton's second law, summation of forces. For which one? Be careful here. Be careful. First, start with degree of freedom. X. I'm going to start with X. The small mass. This one. Degree of freedom X. Well, you have to apply Newton's second law here. And you have to apply Newton's second law on the pulley separately. Okay, because we have 2 degrees of freedom. And then after that, you can substitute one in another because x is depending on theta and theta depending on x. I hope this is clear, okay? So we will start first with degree of freedom x. Summation of forces equal the mass times the acceleration. Where is the positive direction of force? Downward. Okay. All right. So how we have only one tension, one force up, equal mass times acceleration x double dot. Okay. All right. And I'm going to call this equation number 1. This is the equation of motion number 1. Okay. Let's keep this in our mind. Okay, this is the only forces. For degree of freedom, theta. Apply Newton's second law. Now this is rotational motion or torsional motion. So we're going to use summation of what? Summation of moment. Around what? Let's call this O, the center. We will call it O, the origin. So the summation of moments around the origin must be equal to mass moment of inertia times alpha, the torsional acceleration. Okay? And what is the positive direction of moment? Counterclockwise. Why? Because theta is going this way. So this must be with theta. Okay? Now apply. What are the moments here? We have from the tension, we have T times R, positive, minus the other one, minus K, R, theta, the force, times what? Times R, the distance. Remember how to find the moment of inertia. Equal to J, given, this J, given, times alpha. What is alpha? It's going to be theta double dot. And this is the second equation of motion. All right. Now, I need at the end, how many equations of motion you should see? I should see one, only one. Why only one? Because x depending on theta and theta depending on x. They are not separate degrees of freedom. Okay? You cannot move x without moving theta. And you cannot move theta without moving x. So you have to substitute one equation in the other one to have only one equation of motion. Okay? This is only valid if you have 1 degree of freedom, okay, in the system. Okay, one student may ask, but I have here x and theta. Yes, but x depending on theta, theta depending on x. There is a relationship between them. Okay? So which one you want to substitute? I'm going to substitute 1 and 2. Substitute 1 and 2. Substitute equation 1 and 2. So what you're going to have, if you substitute 1 and 2, this TR will be how much? Minus M x double dot, right? Times R minus KR squared theta equal to J theta double dot. Rearrange. Before you rearrange, you need to find the question said what, ya shabab? The question said find the equation of motion in terms of theta only. Okay, in any problem, usually he will define what you want, what he's asking for clearly, like in the exam. Okay, here I can ask with theta or x. It depends on the question. Okay, so what you're gonna do now? You need to remember or recall x double dot is equal to r theta double dot. Substitute. So this will become minus m r theta double dot minus kr squared theta equal to j theta double dot. Okay, rearrange. Take everything to the other side. It will be what? It will be m r squared theta double dot, okay, plus k r squared theta plus j theta double dot equal to 0. Rearrange, I'm going to collect these together. R squared plus j theta double dot plus kr squared theta, right, equal to 0. Did you see this equation before? Yes, this is your equation of motion. We got it. Is it the same or not the same as the one that we got before? Kr squared, mr squared plus j. It is exactly the same. Exactly the same. Okay? It must be the same. Otherwise, there is a mistake. It must be the same because we are solving for the same system, just different method. Okay, now the natural frequency from this equation will be how much? Square root kr squared over mr squared plus j. And that's it. Okay? As you can see, which one is more or easier to use in this problem? Maybe this one, the energy method for this problem is easier to use. Why? Because the system is complicated. So energy method usually is very effective, very useful when you have complicated system. What do I mean by complicated system? There are many degrees of freedom, many masses, and it must be, of course, conservative. Okay? And that's all for this example. See you in the last example.